Now, once we have this idea of polar bonds, we need to start talking about what happens when those polar bonds start to interact with each other, or what happens when you have multiple bonds inside of a molecule, okay? So the question becomes, does the polarity of the individual bonds always create a molecule that's polar, okay? So if I have polar bonds, does that mean that I always have polar molecules? So the overall molecule will have sides to it too, okay? The answer to that question is no, all right? And that's what we need to work through is sometimes polar bonds create two-sided molecules. So we have a positive side and a negative side. Sometimes they do not. And we need to be able to figure out when that happens and when it doesn't, all right? Because ultimately, it's more important for us to figure out if a whole molecule is polar or not, because that's going to determine how it acts chemically, not just the individual bonds, all right? So here's how we do it. We look for symmetry, all right? In these two molecules, we have polar bonds, all right? So let's draw the first one up. We have carbon double bonded to oxygen, and we have a couple of hydrogens coming off it at angles, okay? And the carbon to hydrogen bond, if we take a look at our electronegativities, go back to our table. Hydrogen again is a 2.20. Carbon is a 2.55. So between these two, we have a difference that is less than 0.4. So this is non-polar over here. So there's no polarity difference really there. Now there's some polarity difference, but not enough to see a shift in the electrons, okay? So these are non-polar bonds. So the carbon to hydrogen bond here is non-polar. However, oxygen has electronegativity of 3.44. So 3.44 and 2.55, that is greater than 0.4. So the carbon to oxygen bond is polar, all right? So we do see a difference there. Now, if I erase a few things here that's kind of getting in our way, it's getting kind of crowded here. Let's get rid of all this extra junk. Because the carbon to oxygen bond is polar, the electrons that are being shared are going to move towards the oxygen. Now, there's nothing out here that is pulling it back that direction, okay? This does not exist. We don't have anything that's causing this to happen, all right? Which means the overall movement of our electrons still runs in this direction, okay? Which means overall, we end up getting a side of the bond that is more negatively charged and a side that's more positively charged, okay? So this whole molecule has a negative side and a positive side to it, but it's not ionic. So we can't use, or we don't really want to use, just a negative symbol and just a positive symbol because that would imply ionic character. So instead, we use the lowercase delta, which looks like a figure 8 that I didn't quite finish. So a lowercase delta, that's a really bad one. Start over. And this symbol stands for partial. Okay? So we have a partial negative. We have a partial positive in our system here, okay? So that's the symbolism that we can use here. So for a polar molecule, if we were going to actually like symbolize this, we would say that this side of the molecule over here, this side here is more partially positive. This side of the molecule would be more partially negative, okay? Creating a polar molecule, which means when we come to chemistry, it's going to have certain things that it acts a certain way because of that polarity of that molecule. Now, the other example that we got from our notes was carbon dioxide. So carbon dioxide actually has a double bond as such, and it is a linear molecule, which means it's in a straight line. So we have carbon in a polar bond going this direction, and we have carbon in a polar bond going that direction. Remember, we learned from our last example that these were polar bonds, okay? So in this case, we have this polarity pulling electrons this direction, but we also have them pulling it this direction, okay? So now that we have two different directions, what happens is these two things actually cancel each other out. So this polarity and this polarity cancel because they pull in equal and opposite direction. When you pull in equal and opposite direction, we get a canceling effect. So even though this molecule has polar bonds on it, so yes, the bonds are polar, for sure. Okay, those bonds are polar. The molecule here results in being non-polar. Okay, because these bonds cancel each other out. They go at equal and opposite direction. So the trick for us is, how do we tell when we get to a molecule if those polar bonds are going to cancel out or not? That's the trick, and that's what we got to learn, okay? So let's go back to our slideshow because I got some more information for you on that, all right? To do this, we look for symmetry, all right? This molecule is not symmetrical. This one is, all right? That's our first step. Things that are not symmetrical, if they have polar bonds, are going to produce polar molecules. Things that are symmetrical, even though they have polar bonds, might produce a nonpolar molecule, okay? So here's some rules to help us out. So first rule, if your central atom on a molecule contains unshared electrons, okay? So if you have any unshared electrons on a central atom, you're going to be polar, no matter what, all right? Let me give you an example of that. So probably the most common example that we see of a substance that has unshared electrons on its center atom that we're most familiar with would be water, H2O. We have seen water drawn this way before, where you have this, let me erase that so it's got out of our way here, where it has kind of a bend to it. And the reason why it always has a bend or a kink to it is because oxygen has a couple other unshared electrons floating around on the top of it, okay? These unshared electrons actually create space or push out space that forces the hydrogens down into a kink, okay? As a result, these unshared electrons right here create a lot of negative charge on that center atom. So a lot of negativity there, which makes this whole thing polar, all right? So the simple rule is, if you see electrons that are not part of a bond, they're unshared on the center atom, okay? So oxygen here is our center atom. This guy right here is our center atom. If that's the case, always polar. Because you can't have a molecule that's symmetrical with these electrons here on it. So because of these electrons here, that's creating electron density up here. Because of them, we cannot have a symmetrical molecule. So you have to have a polar molecule. Rule number one. Rule number two, molecules with a single central atom with all the same atoms surrounding it will be nonpolar, even if the bonds are polar, okay? So an example for that is, let's say we go back to boron trifluoride. We did that one before. Okay? And boron trifluoride, if I bring in some electrons here for us, would be something like this. And in this case, we have, one bond, two bonds, three bonds. And we know boron can do this because it can reduce its octet. And everything around the outside, we have a single fluorine, another fluorine, and another fluorine. Everything is the same around the outside. With that, we now have symmetry, okay? So even though we have some unshared electrons, here and here and here and all over here, because they're not on the center atom, they don't matter. The outside atoms we don't care about, okay? Because there's no unshared electrons on the center atom, and because everything else is the same here, we have a nonpolar substance, okay? So that's rule number two. Molecules with a single central atom with all the same atoms surrounding it will be nonpolar, even if the bonds are polar. Now, the exception to that is if you have unshared pairs of electrons, go back to number one. Number one trumps number two, you can still be polar, okay? Number three, if you have all nonpolar bonds, your molecule is nonpolar, all right? So that would make sense, right? If there's no polar bonds, how do you create polarity, okay? There is an exception to that. If you have these unshared pairs of electrons, they create the polarity because they create a negative region around that atom by being there on that center atom, okay? So basically, rule one trumps rules 2 and 3, okay? And then rule 4, if a molecule has polar bonds, but those bonds are symmetrically placed and are of equal strength, the molecule will stay nonpolar, all right? So here we're saying if things are different, that's okay. If you have symmetrical scenarios and you have equal strength, then you can have a nonpolar substance, all right? As always, the exception is rule number 1 trumps rule number 4, okay? Now there is a special note. So if you take a look at molecules that have 4 bonding locations, so I have a picture of it right up here where we see here's a carbon and there's 1, 2, 3, 4 bonding locations coming off that carbon. Now in this scenario, you may think that this is going to be polar or nonpolar. I'm not sure what you guys are thinking. So let's take a look at it and we're going to draw this thing up for us, okay? So let me erase a couple of things on my screen so we get kind of a clear screen to look at. In this case, I have carbon in the center. Let me get this thing going here. I have carbon in the center, and I have chlorine coming off it in 2 locations, and I have fluorine coming off it in 2 locations, okay? So now there are 4 bonds coming off of this, okay? You may think, well, there could be some symmetry here because the way you drew it, Mr. Dirksen, is you put the chlorines on one side and you put the fluorines on the other side. So in that case, yeah, sure, the fluorines are more electronegative, so this side will get negative, and this side will end up being partially positive because you chose to draw the chlorines on this side and the fluorines on that side, right? That's valid, okay? Potentially, I could have drawn it like this, right? Where I could have said, instead, I'm going to move these around a little bit, and I'm going to put the chlorines on opposite sides of each other, like we see on the screen, and fluorines opposite sides. So if that's the case, Mr. Dirksen, then they would be symmetrical, right? Because in that case, you know, the polarity going this direction and the polarity going this direction in comparison to the polarity going this direction and the polarity going this direction could cancel out because red would cancel and blue would cancel, and it would be fine, okay? The reality is that never happens, okay? And that's what this special note is talking about. So in this case, this is only a 2-dimensional representation of this, okay? And what we want to make sure is that we're comfortable with is that in reality, when we have real molecules that are 3-dimensional, so for example, if I choose this molecule, okay, if you have 4 bonding locations coming off of a center atom like you see here, this never is 2-dimensional. It's always 3-dimensional. So there's never a time where you have, let's see if they have an example of that for me. They don't actually. Bummer. Okay. There's never a time where anything really sits opposite of each other. Okay. So these two, if we say that these two are the chlorines and these two are the fluorines, no matter how I rotate it around, the fluorines are now coming out at me. Now the chlorines are over here. There's always sides to it. Okay? So the only way we can get a nonpolar molecule is if all 4 of these things are the same element. All right? If any one of these 4 is a different element, that's going to create polarity because it is not a cross. It is not a T that's inside of here. It's a 3-dimensional shape, okay, that it creates instead. Okay? Because of that 3rd-dimensional shape, these things are always want to stay equal distance away from each other as we take a look at this guy. And as a result, let me go back to this model here. As a result, you can't get them symmetrical if you don't have the same elements on the outside of that. All right? So that's one thing we just got to be aware of as we take a look at that is that special note. Okay? So we draw this up, and I show it here too. You see these are kind of a yellow color. These are kind of a green color. So you cannot have them crossing each other. This molecule here would be polar because the green side would pull differently than the yellow side, and that would create polarity here. All right? So that's kind of our rules. Now with this stuff and any of these kind of things, you need to practice it. Okay? So in the next couple of slides here, we're going to go through some more practice for you. Okay.